Behind me here is derivation for the rocket equation. It's an integral part of rocket science, which is an interesting term because usually we use rocket science to describe things that we have difficulty understanding. I think we could do a little bit better than that though. So I was thinking, if you wanted, you could make a rocket on your own. It wouldn't take very much at all. It wouldn't take any of this. In fact, it would just take a few bowling balls, actually. Because according to Newton's third law of motion, for every action, there's an equal and opposite reaction. If I throw a bowling ball downwards, the opposite reaction will thrust me upwards. So imagine that I stand holding a bowling ball. If I thrust the bowling ball downwards, my momentum will equal my original momentum, 0, because I'm standing still, minus the momentum leaving the system. In this case, the mass of the bowling ball multiplied by the velocity of the bowling ball relative to me. Since the velocity is negative or downward, that'll result in subtracting a negative momentum or positive momentum given to me. If I did that, I'd probably feel my body lurch upward, but I wouldn't leave the ground. That's because the force of gravity is also acting on me. However, if I stood on a scale and threw the bowling ball downward, the scale would show I briefly became lighter. I could overcome the force of gravity if at the moment I was the lightest, I immediately threw a second bowling ball. The resulting momentum from each throw would be additive, and eventually I would gain enough upward velocity that the downward pull of gravity would no longer be enough to keep my feet on the ground. I would, however, have a new problem. The effectiveness of my first bowling ball would be reduced by the mass of my second bowling ball, and in fact, every additional bowling ball would become less effective because of the extra mass. There's a similar problem with rockets. Now, one difference that you should be aware of, and this may surprise you, but rockets don't operate by expelling bowling balls. They actually expel molecules of fuel. Now, the molecules are smaller, but there are a lot of them. In fact, instead of me frantically throwing discrete bowling balls as fast as I can, the rocket expels fuel continuously. So it takes a little bit of calculus to work out the mathematics, but the principle is the same, which is that the fuel at the beginning of a burn is made less effective by the mass of the fuel stored in the rocket for the later part of the burn. So all of this is embodied in the rocket equation over here. This problem with rocket fuel is something we've known about for a long time. In fact, in the 60s, when we were on the moon missions, the Apollo moon missions, we sent 3 guys into space, but we only had the intention of landing 2. So why take 3 guys on a mission when only 2 people are going to do the important thing? My wife and I live in New York. We have a car, and sometimes we take our car to go on errands. It's not the best idea to go driving in New York, but when we have to, if one of us takes the car, that's kind of an inconvenience because you have to find parking, you have to pay for the parking, and that's expensive. So often it's easier for both of us to go on the errand, and even though that requires the time and effort from both of us, that allows one of us to go in on the errand while the other person drives the car around the block. In a similar way, on the Apollo missions, it was easier to send 3 guys and all of their gear up to the moon, have 2 of the guys land on the moon and run their errands while another guy drove all their gear in orbit around the moon to rendezvous after the mission, pick them up, and go back down to Earth. Saved a lot on fuel to not have to drop that stuff onto the moon and lift it back up again. So far, I've talked about increasing my momentum by increasing the number of bowling balls that I throw, or increasing the amount of fuel in my rocket. This will work to an extent, but there's another part of the equation that I should also try to maximize the effect of. It's the velocity portion on here. Now, when throwing bowling balls, I can throw the bowling balls faster by maybe just working out more, but for a rocket, expelling that fuel, to get the fuel out faster, this is actually embedded in one of the most interesting parts of rocket design, and it's actually something that at first appears a little bit counterintuitive. So this is impressive. This is Saturn V rocket. There are a lot of cool features that I would love to go on about, but what I really want to focus on is the nozzle design. It's interesting because it's counterintuitive. It's called a converging, diverging design. converging, diverging nozzle, and the part that's like in the middle where it converges and diverges is called the throat. And then what makes this interesting is if you wanted something to move fast, like if you wanted fuel to move quickly, you wouldn't want a bigger opening. Like think if you're holding a hose, if you want that water to move quickly out of the hose, you put your thumb on the end of the hose. It makes a smaller opening and the water rushes out quickly. And the reason it does that is because when a fluid is moving at a slow speed, it's most of the time, most fluids are non-compressible. And so being non-compressible, if you block its exit, it can't change density. It has to get out of the way, so it does that by moving fast. So because of that, the converging part at the top of the rocket makes sense, like small opening, fast passage of fuel. But this part is kind of weird. So I want to talk about why that is. To do that, I actually want you to imagine that you are in an airport. So we went downstairs to where they have the space shuttle rocket, and here I want to take a look at this little model because this is a great way to understand why the converging, diverging nozzle helps fuel move faster. So take a look in here. This represents the security gate of an airport, and over here is the arrival section. This is where all the people are arriving. They're all the fuel, okay? And then over here, this is the terminal and the gate at the end. The plane is actually leaving in 5 minutes, and everybody needs to get on the same plane, and unfortunately for them, they all arrived at the airport at the same time. So there's a lot of pressure in this part of the airport. Furthermore, because the security gate has a single file line, people can only move as fast as the scanner will let them through the security check. There's a lot of anxiety, there's a lot of heat, there's a lot of pressure, people are pushing up against each other, they're getting impatient, and everybody just wants to get out. Now, in this situation, the fastest that people can possibly move is going to be limited by the speed of the machine that scans everyone. But suppose there was like a technology advancement where the new scanner allows people to come as fast as possible. There's a point where the limit is no longer the speed of the scanning machine, it's the speed of people to be able to move through a tight space. But what happens is after that security gate, where everything over here opens up, this is where all of a sudden you can bust out into a run, like a full out run. Not only do you have a whole bunch of people who are like anxiously awaiting to get on their plane, but you've got the space to spread out. And the density of that crowd is going to be reduced, but only because they got like jetted through this tight space. So you might think if what you need is space in order to move, why not have the entire rocket just be a big wide open space? And the reason is because you need that pressure to motivate you to get through the gate. Now, the reason for that is because at high speeds, at the speed of sound, the compressibility of fluids becomes more malleable, and all of a sudden the fuel can move much faster, can even spread out, hence converging to get it up to the speed of sound, and then diverging to let it explode outward.